Please can you confirm that you can hear me? All right, awesome, awesome. Okay, so I trust that we're doing good today and all set for this session. I can see a good number of persons on the call. Awesome. All right. Welcome everyone once again to another workshop session at the AISOC of Code 2.0. Now, today's session promises to be super insightful. Of course, this session is specifically for the LLM track participants and also the ML track participants, right? Now, today's session, we're going to be talking about introduction to model interpretability, which is a very critical aspect in your AI systems development. And this session is going to be handled by none other person than Adebayo Oshingbesan. Adebayo is an ML engineer and AI solutions architect who has led several integration of data-driven technological solutions for companies. Now, Adebayo has worked on the integration of technology across various industries, including energy, healthcare, education, finance, red tech, and legal tech as well. Some of his recent endeavors have included analyzing multimorbidity in African populations in Kenya, South Africa, and Burkina Faso in order to equip policymakers with data-driven insights, building AI-driven workflows and agents for complex domains such as finance and legal. And of course, enhancing the tracking and compliance of regulations across 150 countries for multinational companies such as global tier one banks. This is a lot of wow, right? Adebayo has experience ranging from working in multinational organizations such as IBM to scale-ups, startups, NGOs, and many more. Now, this is safe to say that Adebayo has experience across every aspect of industry, right? Adebayo seeks to identify critical challenges and deploy tailored technological solutions that drive efficiency and growth. At the core of Adebayo's current work is minimizing the friction around the integration of classical machine learning techniques and generative AI into the fabric of business operations to enhance processes and outcomes via intuitive human AI verification loops and interfaces. Now, we can tell from Adebayo's solid profile that today's session is going to be a banger. I think in Rema's voice, I should just say another banger, right? Ladies and gentlemen of the AISOC 2.0, please put your hands together for Adebayo Oshingbesan as he takes over. Hello, Adebayo. Welcome
Hello.
on board. Yes, hi.
Thank you, Zion. Hello. It's great to be here. Thank you, Samuel. Thanks for the introduction. So, like Samuel already rightly said, I'm really passionate about building AI systems with this whole idea of human verification, verification loop. So human in the loop, which is why today's topic is one that is very interesting to me in terms of model interpretability. So I'll start sharing my screen. And I'm going to share this notebook after the call so that anyone that is interested can just go play around with it. I kind of like things that are a bit more interactive. So I decided to go with notebooks rather than slides. So just let me know if you can see my screen. Okay, thank you, everyone. Oh, okay, let's go. So today we'll be going through why interpretability matters. Why is this topic important? I'm sure many of you study curriculum and you just decided to go. So okay, I want to do the ML track, I want to do the LLM track. So this is part of the topic that is there, so I'll just do it anyway. But it's beyond what is on the syllabus. We need to kind of understand and get this intuitive feel around why it is important. Then we'll speak about just some foundational concepts. And then we'll talk about like traditional ML interpretability. And now, so I've read this like how many times today, and I did not realize that I had wrong spelling here. Anyway, then we'll do like a bonus section on some level of LLM interpretability via a concept called chain of thought prompting. So let's just get started. So the way I like to think about model interpretability, there are a lot of different definitions and there are a lot of different perspectives to it. But the way I like to think about it is it's the ability for us humans to understand how and why a machine learning model makes its decision. And there are several reasons why this is important. One of it is confidence. It's also very useful for debugging, kind of understanding where your model is failing. One very important part, personally for me, because I've done a lot of work in the area of AI fairness and bias, is to actually detect and mitigate bias. Yeah, so let's say your model is predicting that Black people are more likely to commit crimes, and that's something you want to look at. Is that true? Is that the correlation that your model has learned? Is that perpetrating some like bias that is not necessarily true? That's something you want to look at. Then of course there's this idea of also discovery, which is something I've also done a lot of work in, which is you can use your machine learning model to like extract patterns from data and then look at these patterns, and this gives you new ideas as to the relationship between two variables or two things. So this is what I call scientific discovery. And then there's this idea of regulation in many industries, especially in places like the EU. You cannot use an algorithm or automated decision making without providing some clear explanation as to why your algorithm, your machine learning model made that decision. Because if you do that, you probably get sued. Yeah. So, like I said, there's different explanations. Different people need different things, and what works in terms of interpretability for one use case might not work in terms of interpretability for another use case. And it could also be misleading if it's not validated, right? One of the things I will say today is that different interpretability method gives you slightly different dimensions of the explanations of why decisions have been made. So you really need to think a bit to analyze and to sort of interpret. So you kind of interpret the interpretations of the interpretations that you got from the explainability model. Yeah, so that's part of what your work would be as a machine learning engineer. And so one of the things I have in the notebook here is just installing packages that you might need. Like I said, I'll share this. Actually, let me just copy the link now, so that anybody that is interested can play around with it later. You can probably just make your own copy. So that you can, everything you need in terms of like this tutorial would be in this notebook. So you don't need anything outside of here. And just some basic import, which I think matplotlib, and then of course sklearn for just trying out models. So this finish off just environment settings, and we'll just start with the foundations. So what makes a model interpretable? Yeah, there are different things, dimensions, what I like to call dimension interpretability. There's this idea of transparency. There's this idea of a human being able to mentally simulate the model's decision, right? And a good example of this is if I'm trying to interpret a model that is working with images, I probably want my interpretation, or most definitely want my interpretation, to also be visual in nature. So something that looks like images, because the last thing you want for a human being is kind of telling them, okay, pixel 1 and pixel 10 are close together, or pixel 1 and pixel 10 have this similarity, and they're like, okay, human beings don't look at images in terms of pixels, yeah. So they're looking at it and like, yeah, I don't really understand what that means. So this idea of interpretability is also something that you can think about mentally. And can you understand individual components of like the explanations, which is what I call the ability to decompose the explanations. And one very good thing about machine learning is that we have models that we call inherently interpretable. So you don't really need to do anything. The way the models are trained, the way the models are set up, you can actually look at the decisions directly. And very common one is what we call linear models, linear regression, where you can just train a simple regression model to sort of predict something between classes and all of that. You can use the electric regression model. You should use the electric regression model. But I use the linear regression model here just to show you an idea of what the linear model coefficient is. And the coefficients of that linear model already gives you an idea. In this case, it's very straightforward. It's this coefficient multiplied by the value of your data points that tells you what it is, which is why I actually use the electric regression model here. If I use, I will try to use a linear regression model just to make it easy for you to interpret the weights. For electric regression, you are dealing with log odds and there's some maths, and I did not want to do a lot of maths today. But the idea is you can look at the number, the weights attached to these linear models, and it gives you an intuitive understanding of what is important and what is not. So in this particular example, I just generated data with 4 features. We have three of those features are informative, one is redundant. And you can see that it says, oh, feature 0 is very important. Feature 1 is also important, but not as important as feature 0. And then feature 2 and 3 their weights are very low. So if you were trying to do things like feature selection, which I believe is something you guys would either come across in one of your workshops or should have come across already, you can actually start thinking about the concept of removing feature 2 and feature 3 and seeing if your model, if you don't lose a lot of model performance. And of course, in linear regression, you have this concept of a coefficient to a constant. And so that's what is called the intercept here, and you can see what that value is. And literally, this sort of gives you an idea of what the importance of each feature is, and that's just it. You don't need to do anything extra. This is an example. So a linear model in this case, so there are different kinds of linear models. A linear regression is one of them. A logistic regression of classification cases is another one. Their weights are directly interpretable. In the case of linear regression, their weights are very directly interpretable. For logistic regression, you are dealing with what is called log odds. So it's interpretable, but then you have to do some math to kind of map them back to what some of the things that you need in terms of explaining to another human being intuitively. And then you have another set of model, which is also kind of interpretable, but for a human, can get quickly complex quite easily. And this is one example of this kind of model is a decision tree. A decision tree is your typical if something is true or if something is false, do X, yeah? If it's not, do Y. So that's what a decision tree is. And you can see here that decision tree is a decision tree with max depth of 3. I don't know does anybody want to tell us what max depth is about? Any takers? Okay, hands up if you don't know what max depth is about. So that I just know if I need to explain it. Okay, I think I saw one hands up. So you can think of max depth as the number of decisions the number of if else that you would make for a particular scenario. So let's assume, let us start with features that are a bit more intuitive to us. So let's say you are trying to predict the income of a particular person, right? And then you go, the first thing that you look at, let's say the first thing that you look at is the educational level of the person. And you say, did this person graduate from university or not, right? Okay, this person graduated from the university. If this person graduated from the university, did this person, I don't know, study STEM or not, right? So we looked at the degree, then we look at the course actually. That's the second level. So that's depth 2. Did this person study STEM or not? Then if it's like, oh, did this person study STEM or not? The third decision could be, did this person study STEM, I don't know, in the US or not? So that's the third level. And that's the idea of max depth. It's how many levels of ifs you are chaining before you come to the final decision. And here we can see a max depth of 3. And what that means is that we basically just have 3 levels. So the first level here, we are using feature 0 and is checking whether feature 0 is less than a particular amount or not. And at this level, we have 700 samples, and you see that the way decision trees work is you split according to like different criteria. You could split according to what is called a Gini or an entropy. The way I want to think about this is how much decision you get, how much information you get by splitting with that variable, with that value. One thing that you quickly see here is here the Gini is 0.5 because true or false, you're actually splitting almost roughly equally between these values. So there's not much information. So you're starting from something like a general case to a more specific case. So you're like, okay, we start from something that's not really discriminative, in this case, feature 0, and you split them almost evenly, true or false. And then you go to something that, then you look at, so the way decision trees work, you can look at a certain feature multiple times. So you're looking at feature 0 again now, and then on the right-hand side, when it is true, you're checking another value, and then you have another true or false in those 2 legs. And then you have the third decisions where now you're looking at feature 1, you have another true or false. And you can see that by the time you get to the last level, which is usually called the leaf nodes, you can see that at that point, you have things have been mostly partitioned such that in a particular leaf, you have things that are mostly a certain class, right? So in the first blue one on the leftmost side, you can see that you have 2 samples, and out of those 2 samples, 0 of them were predicted to be class 0, and 2 of the 2 of them were predicted to be class 1. And then you can go to the second one, and you can see that you have 283 samples. Out of those 283 samples, 280 of those were predicted to be class 0, while 3 of those were predicted to be class 1. And then the idea is that for class 0, for example, for the first box, so the one that has Gini equals to 0 and sample equals to 2, your prediction for anything that falls in that leaf, so after you have taken all of the if statements, yeah, would be prediction of 1 because everything has class 1, yeah. For the second one, depending on how you set up your predictor, you either, in this case, everything is going to be probability of 280 divided by 283 in this case. So that will be your probability of class 0, which would probably be around 90% or so. And then you can go through each of all these leaves, and you can clearly see, it's very clear to see what class will be predicted if you fall into one of those examples. And this is how decision trees work. And you can see that it's quite intuitive. So we can switch out feature 0, feature 1, feature 2 for, like I said, you can switch it out for, let's say, what educational level you have, what course you studied, where you studied, and you can basically tell someone, oh, the reason why we think, so let's assume this is a loan prediction task. And you can say, oh, the reason why we think you would not pay back this loan is because you live in so place, your income is less than so amount, and your last 3 loans you did not pay back, something like that. Or if it was an income prediction, for example, is like, oh, you studied at so and so university or in so and so course, and then you studied in so and so country, and that's why we believe that you are going to earn this certain amount. And you can see how very interpretable this can be. But then the reason why I've got this interpretable with limitations is because of the idea that the deeper this tree goes, the less interpretable it is, right? So imagine you have a depth of 20 instead of 3. Then you are looking at a very deep tree. Then you have a lot of if statements, and then all of those are important, yeah? So you're like, oh, if you went to school at X and you lived in country X, and you studied X and you graduated at X and you studied in the year X, and you can go and you're giving somebody like something that is like 20 features long, which again goes back to this idea of the ability to decompose this interpretability. Then the person will be like, yeah, I can get, it's actually interpretable. You can tell me everything that played into it, but it's not something I can easily visualize. So it's not intuitive for me as a human to visualize like mentally. And then the question is, why don't we just use this interpretable? Like, why would we want to use a decision tree with a depth of 10 rather than a decision tree with a depth of 3 all the time? Yeah, like, why are we making our lives more complex than it needs to be if we want to interpret things? And the idea is back to something called the accuracy interpretability trade-off. So this is not always true, just to be clear. Sometimes you don't have to trade off accuracy for interpretability, but for most times you need to do it. Like, more interpretable models are usually simpler than less interpretable models, which then means that for you to get better performance, you want to use the less interpretability models, which is the entire like conundrum of the machine learning interpretability space here. You want your models to be as accurate as possible, while also be as interpretable as possible. And I'll give you like a very dummy example, yeah? If, let's say we wanted to do a loan prediction scheme, and basically our decision is that we would always reject everybody that applies for a loan, right? And our explanation is that, yeah, no matter who you are, we reject you. That's a very interpretable model, yeah? Like, because there's nothing to learn, there's nothing to interpret. Like, it's basically, if you apply, we reject you. That's the model. And that's very interpretable. But that's kind of not a very accurate or a very useful model, right? Because you're like, okay, what's the point of the model? Like, you don't have to learn it. You don't have to train a model that learns reject everybody, yeah? You want a model that is able to accurately predict people that would actually not default on loans, which is accuracy. But then you also want to be able to tell people why you rejected them, right? Because if somebody applies for different reasons, maybe for customer relation, again, like we said, it may be for regulatory reasons, like we said. But if somebody applies for a loan and you reject them, you want to tell them, we rejected you because your credit score was below 600, right? So you want that balance between like accuracy and interpretability. And what I'm just showing here is just like, again, this is a dummy example, but I think it drives home the point, which is, if we look at the results from like a decision tree of depth 3, we see that the accuracy is around 91%. If we use a decision tree of depth 10, the accuracy goes from 91 to 92. If we use what is called an ensemble, so a random forest, if you are not aware, is basically a combination of decision trees. So if we use a random forest at depth 3, at depth 10, sorry, that should be a deep random forest at depth 10, our accuracy goes from 92% to 96%. So we have a more accurate model. And like I said, a random forest is literally just, so this is what we have seen something like this before. This is what a simple tree or depth tree looks like, similar to what we have seen before. But then this is what a tree of depth 10 looks like. And even visually, you can kind of see how much more difficult it is, kind of like even understand what is going on here. And then for a random forest at depth 10, you basically have, depending on how many trees you have in the forest, you basically have 100 of these. So I just showed this is depth 3, and I'm showing just the first and the last trees in depth for the shallow random forest. And basically what you want to do when you want to interpret is you have to take each of the explanation for each of the three, right? And then you have to take that for all the three. So you have 100 explanations, and then you have to kind of compress those in such a way that it is still kind of like interpretable, like a human being can still kind of understand, which is a very difficult problem, because then you have what is called an and of ors, yeah, because each tree is an or, and then each like all the trees, the relationship is ors, then each tree is an and. So you're saying if feature 1 is less than this, and feature 0 is less than this, and feature 0 is less than this, or if feature 0 is less than this, and feature 1 is less than this, and feature 3 is less than this, or, and you're going to have 100 of these. And that's for a tree that is depth 3. Now imagine a tree that is depth 10, that takes you to 96% accuracy, right? You have something that is 10 string long for one tree, and then you have 100 of these. So basically in your explanation, you have 1,000 things. That's not something that humans can intuitively understand, yeah, which is one of the main points and the main goals of interpretability. Any questions so far? Is anybody lost as to? I think I've tried to kind of motivate why we need to do, like, go a bit further in interpretability. I don't know if anybody has any questions so far. I can't see any in chat. So I'm going to guess everybody is good. Okay. So if we want to use these complex models, yeah, that are not kind of interpretable, because still I still showed like interpretable models, but if we want to use complex models that are not really interpretable, but we still want to interpret them in a way that satisfies this criteria that I spoke about. Not necessarily satisfies, but at least helps us to. It's a bit transparent. We can still understand the model mechanism. We can kind of intuitively understand and mentally simulate how the model is doing its computation, and we can still kind of decompose the individual components. How do we go about this? And this is where what I call traditional ML interpretability comes in, which is very similar to what you currently have. So what traditional ML interpretability does is, if we go back to these inherently interpretable models, rather than having, for this deep tree, rather than having, for this random forest, rather than having 100 of these, is there a way we can collapse all of these 100 into something that still looks like this? Still intuitive to understand, very, I would say very straightforward, yeah, intuitive to understand without all the hassle around this. And that's where like a lot of smart people have kind of done a lot of work to kind of help us understand it. So one of the things that people have come up with is this idea of what is called feature importance. And you can think about this very similar to what we have in the linear model weights that we spoke about earlier, which is, it's basically collapsing all of those 100 trees that I just showed you. I mean, I did not show you all 100, I showed you 2 out of 100. but kind of collapsing all of them and it's giving you something that is very straightforward to understand, which is a measure of importance for each of them. And what this is saying is, if I look across all of the 100 trees, and so there are different ways to compute feature importance. I don't go too much into the math currently, but the idea is that what this is saying that I could average out all the results of like how important all of them are across each tree, and I can give you just one picture of what the overall importance is for feature 0. So feature 0 here is almost 70% in terms of the importance of the feature out of 100%. Then you can kind of see what the others are. So this is telling you by far that feature 0 is the kind of like the most dominant feature in terms of predicting how important this is. And you can kind of get a sense of these when you look at the trees and you just count how many splits were done by a feature. So if we look at one of these trees, for example, tree 1, if we look at just a simple way to count importance is just how many times was it split by, right? How many times was this feature important for the model? And if you look at tree 1, we can see that, okay, there are 1, 2, 3, 4, 5, 6, 7, 8. There are 7 of these, and out of those 7, we can see feature 0 in 1, 2, 3. So 3 out of 7, we can see feature 3 in 2 of them, we can see feature 2 in 1, and we can see feature 1 in 1. So, okay, that's interesting. If you go to the other side, you can also see, okay, out of 7, you can see feature 0 in 2 of them. You can see feature 3 in 2 of them. You can see feature 1, I think 2, and feature 2 one time. Okay, feature 1 once and feature 2 one time. And you can kind of start getting this idea of just by counting how many times the model used this particular feature to split, you can kind of sort of give you an idea of how important this is. Of course, there are other ways, but this is just like dummy, very easy ways to do this. And when you use any of these techniques, there are a couple of them, you can come up with this kind of figure. And that's what this is. This idea of feature importance, very straightforward. It's basically collapsing everything that you have and putting them into one. Yeah, very good question. Can't one train a simple tree for interpretability, but use deep tree for prod? Yes, you can. But there are 2 ways, and you have brought out something that a lot of people have kind of like tried to do, which is you can train a deep tree for your prediction, and you can then train a shallow tree to kind of mimic the reasoning of the deep tree, right? And see how accurate they are. So there's a lot of packages in Python that actually does this. But then one of the things that you'll be missing out of is because the shallow tree is a simple model, it probably will not be able to approximate the accuracy of the deep tree, the decisions of the deep tree. One. And then you come back to this question of transparency, right? Is your simple tree actually telling you how the decision was made in the deep tree? Maybe, maybe not, yeah? You can't really say for certain. Does that make sense, Bruno? So yeah, so this is something that people do, but it's something that, depending on like, and it's something I've done myself also, right? Not just deep trees, you can come up with what they call like surrogate models. That's what they are called, which is kind of like a model that tries to mimic the behavior of another model. But then you're back to the question of, are you sure it's actually mimicking it, or the model has learned something else entirely and it's just telling you something else? So one of the things that kind of jumps out of you is, let's imagine you are trying to predict whether someone will pay back a loan or not, and feature 0 is, I don't know, the sex of the person or the race of the person. You as an ML engineer, an AI engineer, that should start giving you red flags, yeah, because you have to. So there are 2 bits. There's the fairness and bias part of this, yeah. Yeah, you can set a threshold. So you can remove features based on a certain threshold. That's something you can play around with. So Bruno's question was based on the feature importance. How can we set a threshold for the important feature? You can decide that, okay, you only care about features that have an importance of more than 0.2, yeah, which would eliminate all the features here, apart from feature 0, right? So when you have this kind of scenario in real life, there are two things. Can you rephrase your question, Bruno? I don't think I fully understand it. There are two things that jumps out at you, which is one, is feature 0 something that should not be, the model should not be taking this importance, right? Whatever the feature 0 is, right? That should be something that jumps out at you very quickly. And feature 2 is the concept of what is called target leakage or data leakage, which is feature 0 telling me something about my target that it should not be telling me, right? So example of which, and I've seen people make like the classic mistakes, yeah. Like you want to predict if somebody's income is above 100K, let's say that's the target. And then as part of your prediction, you have salary, and salary is 100K, is there. And it has almost a one-to-one correlation, or it should have a one-to-one correlation as to whether their salary is greater than 100K or not, or their income is greater than 100K or not. The question then is, when you want to actually predict in real life, would you have that information? Like if you get a new customer and you want to predict whether their income is above 100K, would you actually know their salary or would you not? In some cases you would, which is probably fine. In some cases you might not, yeah? So the question then is, this feature that is so important, should it be this important? Either from like an accuracy perspective, from what you know about the domain knowledge, from bias and fairness, yeah. Like if you have things like what is called protected attribute as this very important feature, then let's start thinking about what has your model learned, yeah. As your model learned things that you should not be learning, right? And if that is the case, how do you mitigate against that? Or have you mistakenly added information into your data sets that you would not have at prediction or inference time, meaning you have leaked what is called target leakage or data leakage. You have leaked information from the future into your data set and you're training on that, and that's also not good. So that's one of the other advantages of this. Like you can look at this and you can start getting an idea of whether there's an issue with your training methodology. So this is one way you can do, like I said, there are different ways for you to get this graph from all the trees. There's entropy, there's Gini. You don't really need to care a lot about the math, but like they're just different ways, and each of these ways will give you slightly different diagrams. And you just need to be able to understand what this tells you. The other thing you can do, so this kind of feature importance, they're called built-in because like you can just basically calculate them from the model itself. So it's kind of similar to what we have for linear regression, yeah, or for decision tree, where it's kind of coming directly from the model itself, but there's some form of additional logic on top of whatever the model provides. So linear regression and decision tree will just give you can use directly what comes from the model. But when you're dealing with like a random forest, for example, you have to start thinking about how do you combine things from 100 different trees or 1,000 different trees in a smart way, which is like there's different mechanisms, there's Gini based, there's entropy, you can do counts, you can do cover. Like people have different ways of like doing that aggregation, like I spoke about. But there's also the cases where like you cannot use your things from your model directly, yeah. And one of the things that you use in this case is what is called permutation importance. And the concept of permutation importance is actually very simple. It's kind of a very intuitive one. Is like if I just shuffle this particular feature, like if this feature is random, right? So if it does not make any sense. So, and the way you randomize is you just shuffle that particular feature. Or you can set it to 0, set it to some random number, yeah? If this feature is meaningless, right? How worse off is my model? And that's the idea. You can do this a certain number of times and basically average average, do some interesting maths, and basically average that and come up with a number, right? And that's the idea of permutation importance. It's this idea of what happens if I remove this feature from my model, what for my decisions, for my model learning, what would happen? Will it learn? Will it be better? Will it be worse? But how much better will it be? By how much worse? And how do I regret this? And we can see that the order is still kind of similar, in which that in terms of feature importance, feature 0 still seems to be far ahead of feature 1 and feature 2 and feature 3. But one of the interesting things you kind of see now in like when you use functional importance is that feature 1 and 2 seems closer to each other than they are when you actually looked at the random forest feature importance. Yeah. Then you look at the random forest feature, it kind of tells you that okay, feature 1 is sort of like 2 times more important than feature 2. When you look at here, you see that it's actually super close, like because if you look at the uncertainty lines, right, it kind of tells you actually technically we don't even know, like we don't think that, at least using this methodology, we don't think that feature 1 and feature 2 are that different from each other in terms of importance. And that brings home like the second point that you should always remember, which is different methods actually, interpretability methods actually can sometimes give you conflicting information. And it is your job as an AI and ML engineer to kind of understand why and to understand which interpretability method fits best for a certain scenario, right? Like different methods can give you slightly different answers. They should not give you too different, like it should not be like, oh, so badly different, but like they can give you slightly different answers, and they're still like human judgments here, right? In terms of like looking at these interpretability methods and kind of understanding which one is best for a particular scenario. It's not just plug and play, right? It's not just, oh, this is the best all the time. So yeah, these are some of the things you can do. Then there are other techniques also called, there's one called partial dependence plots. And the idea of partial dependence plot is it's sort of very similar to feature importance, but it kind of gives you a more, what I call a more 2D view of how your feature actually affects your prediction. So what this is telling you, so I plotted the feature importance of feature 0 and feature 1. And what this is telling you, if you just look at it, is actually our probability of the predictions that would stay constant most of the way for any feature less than, I don't know, 0.75, right? But then after that, it starts rising a lot. And then once you get to like once you get to like 1.0, it also stops rising, right? So it basically tells you, okay, for this particular feature, so the first one, the other method that we have actually looked at so far just tells you on average what is the importance, yeah? But what this is telling you that actually below -1 and I'll say like minus 0.75 and I'll say like 0.75, this feature actually does not matter, right? Like if outside of those two range, it does not really matter. It only matters in this very narrow range of 0.75 to minus 0.75 to 0.75. And this gives you another, what I say, it gives you another perspective as to the behavior of your model, right? Because it's telling you that for your model, outside of this very narrow range, this feature really does not matter, right? And then you can start understanding, okay, why is this the case and all of that. And then you see you see something similar also on the left side here, which is it goes up, it's up, then down, it goes down between a certain range, then it goes up, then it jumps up, then it stays constant. And again, the idea is it tells you how your model prediction is within certain ranges. And that's the whole idea of the partial dependence display. So mathematical data shows you the marginal effect of a feature on prediction. And the biggest issue with it, even though I did not mention it, is it actually assumes that features are not correlated. So that's one of the biggest issues, partial dependence plots. And in the real world, your features are actually correlated. So you really have to be very careful when you're interpreting this. Over the past, I would say 10 or so years, one of the most popular interpretability method is what is called Shipley values. And there's a package called Sharp that basically offers it. There's like Shipley additive explanations, and it's a very, I really like the math in it. It's a very nifty math using like game theory and all this interesting stuff. And the basic idea is that you are trying to understand the contribution of a certain feature in the presence of other feature, which is why it's like, from a mathematical point of view, it's probably one of the most rigorous explanation method that we have, and it's really popular. It works for image, it works for tables, it works for tests, so people like to use it a lot. And usually my advice is that your first go-to usually for interpretability should probably be the Sharp package. Yeah, just try that out. If it does not work, then you can start looking at other things. Of course, if your models don't have like implicit interpretability mechanism in that case. And one thing I've done is you also have this idea of Shipley values. You also have this idea of partial dependent plots in Shipley values. And again, just to drive on the points that I made previously, we can see that the graphs, even though it looks similar in shape to the partial dependent plots, the previous partial dependent plot that I showed, which I can't find anymore. Okay, this is it. It looks very similar in shape, where the actual exact effect in terms of value comes in has changed. So this is much closer to like 0.25, where previously we had minus 0.75, I would say. So again, it gives you like the same kind of general picture, but you can have like these nuanced differences depending on what explainability method you use. And this is something you as an expert would need to take into account when you're kind of explaining and kind of understanding what is happening. And also, Sharp also has this concept of something similar to what I showed above already, which is like this summary bar-like plot. And again, we can see that, okay, looks very similar, but to what we had above, yeah. But again, like we see here, feature 1 seems to be far more important than feature 2, but then Shipley value seems to agree with the permutation importance bits that we did previously, that kind of said that feature 1 and feature 2 are kind of similar in importance, and feature 0 is way more important, right? And this is how all of this this is how you get like differences, right, in how these things are set up. And then what you start thinking about is, so far we kind of have been looking at, on a feature level, what features are important or not. But then usually you also need what is called, so that's what is called global interpretability. They're like, in general, how does my model learn, or what's my model doing? But then you need this concept of local interpretability, which is for a particular prediction, what features are actually affecting my model, just for one prediction. And you can see that even though the view globally can be different, locally for one particular prediction, the view can be way different. So we saw above that feature 0 is globally is the most important. For this particular feature, actually feature 1 is the most important. For this particular instance, feature 1 is the most important, right? And that is one of the big difference between like local and global. Like the fact that something holds globally does not mean to hold locally, and the fact that something holds locally does not mean to hold globally. So depending on what kind of explanation, what kind of use case you have, which interpretability method you use can vary differently. So if the idea is to, I don't know, provide interpretability to like a customer as to why maybe their loan was rejected, then you definitely want to go local. So you want to say your loan was rejected because of this particular thing that is about you. No customer really wants to hear yeah, in general, we don't give people above the age of 30 loans. Like, you're like, yeah, but I'm 27 or I'm 13 or I'm 20. Who cares? Yeah. Like, why should I care about the fact that in general you don't give? This does not really affect me. I'm not 30, right? Or like in general, if you don't have a college degree, you're like, oh, in general, we have a college. If you have a college degree, we give you a loan. You're like, yeah, I have a college degree, but you're not giving me a loan. So why is this important to me, right? Which is where local importance comes in, yeah. And for that use case, you want local importance. But for like, let's say that you are doing this for regulatory purposes, or you are doing this to audit for bias, for example. Yeah, local importance is probably important. But let's say that your model is biased for one person out of a million population. Nobody's going to sue you for that, yeah. But if your model is biased for 900,000 people out of a million, but it's good for 100,000 people, and you show that, oh, because it's good for 100,000 people, it's fine, then people are going to sue you. So there's this concept of what do you use when, going back to what we spoke about in the introduction, yeah, like it's really important to think through all of these things. And I think here I was just trying to show you, like, okay, this is what the weights. So how linear models work is that you have this idea of linear model coefficient times the actual data points and then the intercept. And I was trying to see whether there was some kind of correlation between like feature 0 and feature 1. And you can see that feature 1, yeah, they both have negative values. So this is minus 0.37, this is minus 1.9. But again, these are two different models, so not directly comparable. But even when you're using two different models, you can see that they kind of go in the same direction in that sense. So one other thing that people also use, one other popular explainability method that people use for local interpretability, because LIME, you can't do global interpretability, is this concept of LIME, which is very similar to the question that Bruno asked earlier, which is, okay, why can we not use simpler models to kind of train and understand for interpretability purpose a more complex model? And LIME basically did this in a way that rather than try to understand the performance globally, it's just going to say, for this particular sample, what happens, let me just reconnect. What happens if you do what is called local permutation of the samples? So very local, so it's very, for this particular sample, what happens in terms of explainability. So you cannot really use it for global explainability. Also, it can also be a bit unstable, which is why many people don't really use it. But I found it also very useful in the real world for like local interpretability, which is, it kind of tells you this idea of using simple models for very local permutations of the particular sample you're looking at, what is important. And one of the things that jumped out at you very quickly is, for the same sample we're just looking at, this is the kind of like importance diagram for LIME, while Sharp had something that looked completely different, which is feature 0 is not as important as feature 1, but LIME is like feature 0 is really important compared to feature 1. So again, this is where like your intuition and your understanding as an ML and an AI engineer comes in, trying to understand what's happening and what should be set up. And finally, there is this concept of counterfactuals, and this was one of the places I had to just like introduce very simple maths notations and all of that. But the idea is, this is really important when you want to find a small change such that you change the prediction of the model, right? So let's assume that, again, let's go back to the loan example, and let's assume that your model has learned that if somebody is less than 30 years old, we should not give them a loan, and the person is currently 29. What counterfactual explanation does, it doesn't really tell you, oh, we did not give you a loan because you are 29. It says, if you were 30 years old, we would have given you a loan. right? And this is actually very useful in places where you want what is called actionable interpretability, which is you want to be able to tell people to do X so that they can change you want to tell people that they can get better outcomes or a different outcome by doing X, right? And this is very popular in like online spaces, yeah, where like you do like thumbs down and thumbs up, or you do likes and dislikes, or you share and repost, those kind of things. Sometimes they tell you maybe on LinkedIn, or I don't know what other social media people use, but like if you don't want to see this kind of post, yeah, and like the idea is like people can be able to like give and action can do something to get a certain outcome, and that's what the idea of counterfactuals are. And I basically, so I've done a lot of work on counterfactuals. So I find them very interesting. I basically just gave a very simple vanilla counterfactual algorithm here, which is we try to change the feature a bit. So we look toward the feature and we try to increase them small, in trying to increase it or decrease it a bit, and try to see whether that changes decision. And we do that 1,000 times and see whether we can find something, right? And this is like one of the most basic algorithms you can do for counterfactuals. And there are a lot of libraries out there that does like more interesting stuff. But then what this is saying is, so if we go back to, if we treat this as like a loan prediction item again, what this tells us is that, oh, if this user can just change this value from 0.1 to 0.2, then their loan will be approved, yeah? Whatever 0.1 to 0.2 is, right, in the real world. And then there's a lot of constraints here, like it might be that, oh, if this person can get younger, the person's like, okay, yeah, I can't get younger. Right? Okay, if it's like, oh, we don't give loans to people below 30 years old or above 30 years old, right? And the person is already 33. You're like, okay, yeah, I can't change my age, yeah. So what can I do? And that's when some interesting algorithms usually come in, what is called counterfactual, right? Which is you want to think about what is realistic and what is actionable, and then there are mathematical ways to kind of formalize this to get like examples that would be realistic and for people to action. And that's where like a lot of work in this domain is. But on the basic level, it's very, very simple intuitively, which is you want to change a certain feature by a bit in certain directions, and you want to see whether that will change the model prediction. That's just the simple definition of a counterfactual. And the idea is that you can use that to give people actionable explanations. So if you want to get a loan, you have to do this, right? And in terms of like classical techniques, these are like the major themes and major ideas that people have. I don't know if there's any questions so far. No questions. Collapse this. Okay. So if there are no questions, I think I'll just round up with, and this is probably something you have already seen in your LLM class. So even though like one of the most complex models to kind of understand today is a large language model, there is this concept of chain of thought prompting that can help you to kind of get some idea. Again, it's very similar. It does not really fully satisfy all the things that you want in terms of explainability. It can kind of give you very, very some idea as to why the model thinks a certain what's it called, prediction should be made. And of course, there is the risk of hallucination. There have been some research that actually showed that chain of thought may not reflect the true internal reasoning, but then that's probably also true for humans, yeah. But the idea is very simple. Is rather than just say, and I think nowadays a lot of people use LLM for classification or things like that, yeah. Rather than say something like, just classify. So rather than just ask for the labels only, you can add a field in terms of like, or where you prompt and say, provide or think step by step, something like that. You can do that. And what you then have is you would have something of this nature, right? So you say, so we're trying to classify whether a tweet is a message is a spam or not. Yeah. And you have, okay, hey, Jason, you're awesome. And it's like, okay, the text is a friendly message directed. It does not contain any promotional content or suspicious elements that typically classify a message as spam. So basically, this is why it's saying that it's not spam. It's like, it does not contain any promotional content or suspicious elements. And when I read this, it does make sense. Yeah. This is something I can send to my manager or a regulator that asks, okay, why was this not classified as spam? I can just send this off. And then you have this other case where the text is, I'm a Nigerian prince, I need your help. And you can see the model said, present a classic scenario associated with advanced fake scams, where the model, where the sender poses a well-known individual asking for help, typically in form of money or personal information. This message is designed to manipulate the recipient into providing assistance to financial gain, blah, blah, blah. And that kind of gives you like an idea of why the model thinks something is spam and why it thinks something is not spam. Again, this does not always hold up in terms of explainability, but it's one of the things I've actually seen that kind of helps you. Some people argue that it improves accuracy, some people say it does not improve accuracy. Isn't that bias? Yeah, I mean, that's some form of bias, but then the model kind of is saying that it's a classic scenario still with advanced fish scam. Yeah. So like it's not saying that because you're a Nigerian or because this thing contains Nigerian. You can change this from Nigerian, can remove Nigerian from here. And I think this thing disconnected earlier. We can rerun this. Let me just rerun this. I need to put in my OpenAI API key. So it will become biased, Bruno, if now that we have removed Nigeria from here, it now says it is not a scam anymore. Then that would be an issue, yeah. Okay, run this. Ah, great. So this is biased. That's a very good find, actually. So this is us suing OpenAI, right? Even though they'll tell us it's not true. So the fact that Nigerian was there, so this is kind of the thing that you kind of have to start thinking about, which is a very good, this is a very good example of kind of things that you have to start thinking about as a machine learning engineer, right? The fact that the word Nigerian was there was actually what made it spam, even though the LLM was like, oh, it's a typical advanced fee, blah, blah, blah. But that's not really the deciding factor. It was the word Nigerian that was there that was the deciding factor. And so this leads us to like a whole what's it called, channel and rabbit hole around bias and fairness, things like token interpretability, attention mechanisms, attention maps, which sort of for an introductory class to model explainability is sort of too complex. Okay, let's try USA. Yeah, that would be fun. I am an American prince. Oh, America does not have a prince, so I probably should change that to British. Yeah, exactly. It knows that America does not have a prince. You know what? Let's see. I am a British. Yeah, the British are up too much money, so I think it will probably find out that is a spam. And that is a spam. Exactly. Let's see where. Hmm, I am an appellate. Let's see. I don't know whether Napel has like a prince or who knows. Okay, so this is very interesting. I don't think this is actually a place, because I don't think they call people from Napel. So he said the phrasing is somewhat unusual and could be part of a fraud scam, which is similar like the Nigerian Prince scam. So it just says scam, it was American, it does say it's a scam with it. So it looks like, so if I was a machine learning engineer on this, I mean, this is a very interesting one. It looks like once you have a popular location plus prince, let's see whether it does not like women or it likes women, let's say, Nigerian princess. Maybe the bias is against prince, yeah? So let's say, okay, so it still says it's princess. So it looks like it was a popular location plus royalty. Uh, let's change this to orphan actually. It should be fun. So now it's fine if you're an orphan. So if it's a popular location plus royalty, so you pretend to have money, that's when it's a spam. Any other combination is not a spam. So these are kind of questions you have to start thinking about. So even though the model is saying a lot of things, you have to start gleaning these kind of patterns, right? So the problem is not that you're Nigerian, is that you're a Nigerian prince. If you're a Nigerian orphan, then it is fine. But yeah, so these are kind of things you have to start looking at, and you have to start. Interpretability is not a one bullet, one silver bullet stuff. Yeah, there's a lot of work that has to go through it. There's a lot of thinking, even as an engineer, to kind of choose the correct interpretability model, kind of understand what's affecting what. So, for example, if your features are correlated, how do you interpret the sharp values or the line explanations? In this case, yeah, we tried different scenarios. We first thought it was because it was Nigerian, then we realized no, yeah, if you actually put American there, it's still the same thing. But then if you put some obscure country or some obscure word, it's like, okay, not spam. So it means that, okay, it's popular location plus royalty, sort of. So these are kind of things that you start thinking about. LLMs are notoriously hard to understand, yeah. So you have to play around with it. But yeah, I think that covers everything I wanted to cover in this introductory class for interpretability. I don't know if anybody has any further questions. Yeah, it's not just. I spent half of my career doing interpretability, so I would have a career if it was just chat and predictions, especially because I don't like chat, yeah. I don't like diagrams, I prefer numbers, so it's a bit more complex, and it's the idea here was to introduce it to like a lot of the main ideas, but there's a lot of rapid which I just remembered I probably did not show you something I wanted to show you earlier. Oh, just give me a second. There was a screenshot I had here in the library that I wanted you guys to be able to go check out later. Okay, so there's this library called Alibi. It has a lot of popular interpretability mechanisms. And it has this very interesting diagram that I like, which is there are different kind of problems. You have translation and regression, and it tells you what interpretability method works for them, and whether it works for tabular, it works for text, it works for images. So this is a package. It also has Sharp that we spoke about. It doesn't have line. It also has counterfactuals. It has Sharp. It has partial dependence. It has a lot. It has computation patterns like we spoke about. So it has a lot of like the major ones, and then it tells you where you can use them and when you cannot use them. So this is a library you can look at in your spare time. Any further questions on this before I hand over back to, I think it was Samuel? Okay, how will counterfactuals work in images? That's a very interesting question because it's something I've actually tried to build myself. The way it works is you want to slightly change the pixels, such that, no, you can't change a pixel. A pixel is just a number, yeah? Like a pixel is just like when an image is represented as a number to any machine learning algorithm. So usually you have a number between, I think, 0 to 255, yeah? That's what a particular pixel is, and you can change that number, those numbers, or a group of numbers in. Let me see whether I still have my work on this. I did some work on this. Should be on my GitHub. Let me just. Oh, I'm blanking on the name of the. Yeah. Okay. Yeah, but you basically you do it by changing pixels or a group of pixels. That's the whole point of. That's how it works. Yeah, if I can find it, I'll share it later. But I don't think I'll be able to find it. GitHub. I can't remember what name I called the repository. But yeah, the whole idea was I was trying to build an interpretability, a counterfactual for actually for images, and it was by changing pixels. I mean, it was a bit, there was some maths behind it. It wasn't just by changing the pixels, but that was a big part of it. Yeah, I don't have it. Can't find it anymore. Yeah, any other questions? Oh yeah, people can actually see my screen. Any other questions on this? Okay. I think I'll hand over back to Samuel. It is, I believe.
Hello, Adebayo. I think you're muted if you're talking.
No, yeah, I said I was just handing over back to you.
All right, awesome. Thank you very much for that fantastic session. It's been a very, very exciting one, and I'm sure the participants have had a lot to take home. Let's see. Okay, so I can see like a few takeaways in the chat. Thank you very much for this very, very insightful session. I don't think would have had any other person do justice to this session the way you did. So on behalf of the AI Summer of Code team, 2.0, I want to say a very, very big thank you for your knowledge that you shared. Thank you very much for your time and for honoring our invitation here at the AI Summer of Code 2.0. We hope that we would get to see you in the next edition of the AI Summer of Code. This has been a very, very exciting one. It's been wonderful. Your explanations have been very, very simplified. They've been very, very simplifying. And personally, I love the examples that you gave. They were very, very relatable. So yes, thank you very much from my side. And thank you very much from the AI Summer of Code team. We are deeply grateful for these insights that you shared. Oh yes, Miriam, I absolutely enjoyed this session as well. I mean, it's a lot. I think for anyone getting started, for a complete novice, this is a session that they would absolutely be able to connect with, right? So thank you very much once again, Adebayo. For those of us at the beginning of the session when we introduced Adebayo and we were talking about him doing a lot of integration of technology, implementation and the likes, it seemed like a whole lot. Now we can see why he was the right person for this particular session. Thank you very much once again, Adebayo. That will be all from here. I believe there are no other questions again, right? So we can call it a night. Thank you very much once again, Adebayo. I'm not sure if you want to say something.
Yeah, thanks for having me. It was fun. It's always nice to contribute.
Yeah, awesome. Thank you very much once again. We look forward to seeing you in the next edition. We'll definitely connect with you on LinkedIn. We'll have your LinkedIn profile shared so the participants can also connect with you,
Yeah,
right?
that's fine.
And then if there are any questions they have, they can put that out to you.
Yeah,
Um,
that's completely fine.
all right, awesome. Thank you very much once again, and have a good evening.
Yeah, bye
Bye.
everyone.